Bam! Mr. Tarrou, in this algebra lesson, we are going to be learning how to solve systems of linear equations through graphing. It's not the most accurate way of solving systems of equations. If your intersection point between your two lines happens to have decimals or maybe even be irrational values, we're only going to be able to approximate what those values are with this graphing technique. So we're going to be moving on to solving linear systems with substitution and linear combination, or your book might call it elimination. You're going to find links to those lessons in the description of this video as soon as those are posted. We're going to be finding or using two techniques for graphing. We're going to be finding x and y intercepts of lines. You find the x-intercept by setting the y-coordinate equal to 0, or the y variable, and you find y-intercepts by setting the x value equal to 0. So over here, remember, when you have a line crossing, intersecting means to cross. So if you're crossing the x-axis, well, an x-intercept, if we just go along here and name a few points along the x-axis, we might have 0, 0, 2, 0, 5, 0. I've only graphed the first quadrant of our Cartesian plane, but of course you can have negative x's and negative y's, like maybe negative 2, 0. And as I name points along the x-axis, one thing that's going to be consistent is every single time I say that the y value is equal to 0, because from the origin there's no vertical movement. And that's why we're letting x be 0, we're letting y be 0 when we go and find those x-intercepts. And likewise, any point you identify along the y-axis is going to have an x-coordinate of 0 because there's no horizontal movement off of the origin. Now, when you talk about trying to find where two lines cross, there's really three situations. Your two lines may not cross at all. You might have two parallel lines, like I'm trying to form here with my forearms. And if two lines are parallel and never touch, there's no solution, because what we're going to be finding is a point where the two lines intersect, one point where the two lines share. Now, if the lines are parallel and they never intersect, we're going to be calling that either no solution, or your textbooks might be calling that an inconsistent system. If your two lines do intersect in one unique point, when you have nonlinear systems, they might intersect more than once, but your lines may intersect in one unique point, and that we'll call an independent system. And then, of course, you could be given two equations where they don't look the same, but once you get them set up for graphing, you realize, wow, these two equations that I was given kind of simplified into the same slope-intercept form of y equals mx plus b. So when you graph those lines, they'll just lay right on top of each other, looking as if there's only one equation or one graph there, but there's actually two. They're just right on top of each other. That's going to be called a dependent system. Or your teacher might just be calling it an infinite number of solutions. So we'll be practicing finding those x and y intercepts here soon. We're going to also, most of the time, we like to solve or graph linear functions by going into slope-intercept form. So we can solve for y to put the equation into slope-intercept form. That's y equals mx plus b. We're going to remember that we're going to plot the y-intercept first. You need to have a starting point. How do you give directions to somebody, to go from point A to point B if you don't know where you're leaving from? I can't give you directions to your local mall if I don't know where you're at that time. Are you going to turn left? Are you going to turn right? Are you close to the mall? Are you far from the mall? Who knows? You need to have a starting point for a set of directions to make any sense. So plot that y-intercept first, and then we're going to move as the slope, or your textbook may be calling it rate of change, directs you, and plot a second point, and then graph the line. We like to say slope is rise over run, and it is, but just saying simple rise over run is really only good for graphing purposes. If you're trying to interpret what your slope means in a word problem, rise over run kind of just falls apart, and you need to remember that slope is a rate of change. You might hear it called a unit slope, the amount of change in y per 1 unit of change in x. We will be doing one word problem in the 3 that we do in this video, and you'll see me talk about that. We have y is equal to x plus 3. Now this equation is already in slope-intercept form. It's already got the y variable by itself, and on the right-hand side, the x term is first, and then our constant is second. So recognizing that we're in slope-intercept form, look for the coefficient in front of the x. Okay, well now slope, in terms of graphing, it's nice to say rise over run. Your slope, you want to have that look like or be represented by a fraction. And when you don't see a coefficient in front of your variable, remember that 1 is the multiplication or the multiplicative identity. When you multiply by 1, really nothing happens. 5 times 1 is still 5. And in terms of algebra, when we have those coefficients of 1, that's why we don't always write coefficients of 1, because multiplying by 1 doesn't really make any values change. It is nice to see that coefficient of 1, however, if you want to identify your slope. So our slope is going to be 1. Now wait a minute, I need rise over run. When you divide by 1, likewise, you don't change a value. 5 divided by 1 is still 5. So we're going to write that sort of invisible coefficient as 1, and then remembering, because slope needs to be rise over run, we want to write that as a fraction even if we don't see one in the problem. So we know how much to rise. This is a positive slope, so we're going to go up, and we're going to run over 1 unit after we rise 1. But where are we going to work that slope from? We're going to work it from the y-intercept. Now, I have videos on graphing using slope-intercept form, and because of that, I'm hoping this is review. I didn't leave myself very much room to write directions and what step you do this and so on and so on. But you do want to do the y-intercept first. So we're going to come up to the y-axis at 3. 1, 2, 3. We're going to be placing a point, and then we're going to move as the slope indicates, which is with a positive 1, rise 1, and run 1. So up 1 over 1, up 1 over 1. And there's no reason to continue the pattern of the slope except for just to make sure you draw a straight line. If you happen to know, by the way, notice that your graph is going to run off the grid if you're given one to graph on your paper. You can go to the left as well, but that's kind of like a backwards or a negative movement. So my overall slope is positive. Now if I go down 1, that's actually a negative movement. So I'd have to counteract that negative movement in the direction of y with a negative movement in direction of x, and down 1 and over 1, well, negative 1 divided by negative 1 is still positive 1. So I could go down 1 and over 1 as well, but I always teach slope as going left to right unless you start running out of space in your graph paper and you need to think about working in the opposite direction. Okay, probably should be using a little ruler. I started to miss there a little bit. Now with my second equation, and we'll do that in green, I have an equation that is 3x plus 4y is equal to 40. Now this is in standard form. This is a very nice form for practicing finding x and y intercepts, but we're going to go ahead and do that on one of the word problems coming up here next. For this one, I'm going to remind you and review with you how you solve this for y and how you put this therefore into slope-intercept form. Now if we're going to put this in slope-intercept form, we're going to be solving for that variable y. It's on the left-hand side of the equation. We're going to identify everything on the left-hand side of the equation. That's the 3x, again, plus the 4y. Maybe highlight a break there, which is the equal sign break in the left and right-hand side up. On the left-hand side, you have a 3x plus 4y. You want to always add and subtract away from the variable first before you deal with that multiplication or division, usually division. You want to do that last in case you create any fractions or decimals. You can just have those show up in the problem at the end instead of dividing everything by 4 right now and maybe having some fraction work that you have to do through the rest of the problem. Over here we have an addition or a positive 3x. We're going to move that entire term over to the left-hand side by applying the inverse math operation, and the inverse of addition is subtraction. And we've got 4y, I guess I'm going to do this one in green, is equal to, now these are not like terms. This is a 40, it's just a constant. There's no variable attached to it. This is negative 3x. So you cannot, you can write unlike terms next to each other, but you can't actually bring them together. This is not 40x minus 3x, so it's not going to be 37x. It's just a constant of 40, going to hang it on the right-hand side with a term of negative 3x. Great. Now we've got 4y equals negative 3x plus 40. with the y on the left-hand side, still trying to look for that y. See, I tried to highlight it in green. Now I'm just writing all my work in green. We're going to undo that multiplication of 4 with a division of 4, the inverse math operation. Now, we teach you that you can do whatever you want to an equation as long as you do it once to each side of the equation. And it looks like I'm really dividing the right-hand side by 4 twice. Think about adding fractions. If I say that you have 1/3 plus 4/3, I'm just giving us a fraction here that already has common denominators. You would combine those to say, well, 1/3 plus 4/3, they already have common denominators. We're just going to add the numerators. See, and you would just recopy that common denominator. You don't add the denominators. And then eventually this comes out to be 5/3. But what I'm showing you here is kind of like, instead of taking two separate fractions and adding them together with that one common denominator, I don't want to, I could, and maybe you could argue it's sort of better to show that one division on the 4 of the 4 on the left and the one division on the 4 on the right, but then students get confused when they have that 1 4 in the denominator underneath the entire 3x plus 40, and I'll have a lot of students incorrectly do something like maybe just 40 divided by 4, and then they let the coefficient of the x stay -3, and they don't divide the 3 by the 4 like they're supposed to. So it's almost like I have taken the right-hand side, I'm dividing that right-hand side by 4 one time, and then I'm sort of undoing that addition and given each term its own denominator. So I'm not dividing the right-hand side by 4 twice. That would be, give me an incorrect answer. But it looks like I am. You can do pretty much anything you want to an equation as long as you do it once to each side, in case that ever had you confused there. So 4 divided by 4 is 1, y, -3/4. If you're calculator dependent, which you really shouldn't be, don't grab that and put it into your calculator and say it's, -0.75. That is going to be really good if you're talking about some kind of real-world application problem and you want to interpret the slope in terms of the word problem, and it would be a unit slope of -0.75, which means you go down 0.75 units for every one you go to the right, and that would be great for, again, doing some kind of summary for a real-world word problem application. But for graphing, going down 3/4 of a unit and over 1 and 3/4 of a unit over 1 and 3/4 of a unit 0.75 and over 1 is going to be very difficult. Or you leave that slope in fraction form and you say my slope, which is rise over run, so down 3 and over 4, my y-intercept is 10, and you do your y-intercept first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It was kind of bad I didn't put a scale on my graph here. I just assumed every tick mark was 1. Down 3 and over 1. Down 3, excuse me, let's try that again. Down 3 and over 4. So from my y-intercept, 1, 2, 3 down, and 1, 2, 3, 4 over. And I just want to make my line straight, even though I really already know where they're going to intersect. So I'm going to do that down 3 and over 4 again. And maybe here where I can have room to write down 3 and over 4, how that slope is moving. And there's your two graphs. We have an independent set here. We have two graphs that are intersecting at one unique point. The intersection, that combination of the x and y coordinate is your solution, and that's going to be 1, 2, 3, 4. And I believe I said 7. 1, 2, 3, 4, 5, 6, 7. Awesome. And now that we have what we believe is our solution, you know, the great thing about a lot of your math tests, the great thing about a lot of them is you can just check your own answer, grade your own paper before you turn it into your teacher. Why wouldn't you want to make sure that what you did was correct? Why wouldn't you want to check your answer? Just today when I was teaching my algebra class, I had a question or an answer that I was positive was correct. I went to explain to him how important it was to check your answer, and turned out my answer was incorrect, and we figured out what the mistake was. So make sure you take the time, check your answer. You need to plug that point of 4, 7 into both of these equations. And a solution is, values that you plug into the equation, and it makes the two sides equal, makes the statement true. So we have y is equal to x plus 3, our x is 4, our y was 7, and indeed 7 does equal 7. Well, now I made sure that that point is on this line. Then I did a bunch of work in green. I really meant to do it in orange so it was all nice and color-coded, but I have some work here for green. Is that yellow point on the green line? Is 4, 7 a solution to this equation? Well, again, our x was 4, our y was 7. 3 times 4 is 12. 4 times 7 is 28. 28 times, that's the tens place, so 28 times 10 is 38, and 38 plus an additional 2 is indeed 40. So that is the end of our first example. One more coming up right now. We got 2 more actually. I love that thing. Okay, so we have our second example here, and it says, again, solving the system of equations. We have 3y is equal to negative x, and we have x plus 3y is equal to 21. Well, let's see. We're going to try and color code this a little better this time. We are going to bring this 3y equals negative x out. This looks a little bit different because there's no constant. It's just 2 terms and they both have variables in it. We're almost where y is by itself, so we're going to go ahead and divide both sides by 3. Just to make this a little bit clearer, I want to highlight again that there's always a coefficient of 1 if, and really technically this is negative 1, except negative 1/3, negative 1/3, and negative 1/3. Those are actually all equivalent. It doesn't really matter where the negative sign is in a fraction. If there's one negative in there somewhere, the whole fraction's negative. So we do have a negative 1x, or there is a coefficient of 1 in front of the x, and maybe your negative's down here on the 3. Either way, I'm going to kind of pull the x off to the side. This is just a teaching step. Remember, when you multiply fractions, you don't need common denominators. You just go straight across the top and bottom. So negative 1 times x is negative x, and 3 times 1 is 3. Long story short, this is the same as basically, not basically, it is. We have y is equal to negative 1/3 x. I like to take the x and pull it out of the fraction to make it really obvious exactly what that slope is. And remember, we're trying to, in this problem, I didn't know I say remember, I didn't really say it out loud, but we are going to try and go into that slope intercept form. So there's no b at the end. Well, what do you add by? Nothing changes. 0. So that means our b value is, I said b and I was going to write 0. Our b value is 0. Our y-intercept is 0. Our slope, which is, again, I'll write it this time, rise over run, is negative 1/3. So we're going to fall 1 and run over to the right 3. And our y-intercept, which is b, as most books, well, all books I've ever seen call it, our y-intercept is equal to 0, or our b is equal to 0. And one more time, you want to, directions are no good. That's all a slope is a direction. How's that line moving? Directions are no good without a starting point. So you want to do your y-intercept first and your slope second. Let's get that y-intercept plotted. Again, that was a y-intercept of 0. Our slope is down 3 and over 1 from the y-intercept. This, by just coincidence, happens to be the origin. Each time going down 1 and over 3. Or I can go up 1, that's a positive movement, but then I can go left 3, which is a negative movement in terms of a horizontal. So it's still kind of like a positive 1 over a negative 3. We get, that is our first line. Now, our second line, let's keep that in orange this time. Now, we can do this with x and y-intercepts. Be a good candidate for that. Or we can do it with slope-intercept form. I know we're going to do x and y-intercepts on the next example or last example. So I'm going to go ahead and put this into slope-intercept form. I also like putting this into slope-intercept form. Like if this were a 20 or a 19, I would absolutely do this with x and y-intercepts. But I know my last step is going to be to divide by 3, and 21 will be divided by 3 evenly. So my y-intercept is going to be a nice whole number. I don't have to guesstimate where it is between two integers. Not that that's something we shouldn't be able to do or should not know how to, I mean, we should be able to do that, know how to do that. But we'll worry about estimating where those decimals are. Keep that to a minimum. So we're going to subtract both sides by 1x to undo that positive 1x. No reason to write that coefficient of 1 unless it just helps you flow through the algebra and get answers correct more often. We have a multiplication of 3 with the y on the left-hand side of the equation. We're going to cancel that multiplication of 3 by dividing everything by 3. We have a slope, again, of, that's a little bit funny. We have a slope, again, of negative 1/3 and a y-intercept of 7. And remembering to plot that y-intercept of 7 first, or any y-intercept first, 1, 2, 3, 4, 5, 6, 7. And from that y-intercept, we're going to do what the slope says, which is go down and to the right. So down 1, 1, 2, 3, over 3. Down 1, 1, 2, 3, over 3. And as many times as you'd like to make sure you're getting enough points to give yourself a straight line. Nice. We're finding out where these lines intersect. Where are they intersecting? They're not going to. They're parallel. They have the same slope. They're both going to fall to the right at the same rate. And keeping on with that idea of unit slope, which is change in y per 1 unit of change in x, our slope is negative 1/3. So for every increase of 1 on the x, the y value goes down by 1/3. And every 1 unit of change in x, it goes down by another third. Well, 1/3 and 1/3 is 2/3. And every 1 unit of change in x goes down another third. And yeah, finally, after I've gone through 3 units of increase in x, I've gone down 3 1/3 or 1 unit. Just throwing some vocab out there if it happens to be important for your class. I mean, vocabulary is always important, but, you know, unit slope. Back when I taught algebra for the first time years ago, I don't think we ever mentioned unit slope. But now as we incorporate more and more statistics in our classes, I think that's the reason why it's becoming more important as a vocabulary word. No solution or inconsistent would be the word for some textbooks, what they would call that. I would say no common points. There's no x and y coordinate like here where the two lines are sharing, where the two lines are intersecting. No solution or inconsistent. I got one more example coming up right now. So here we go. We've got our last example. You have $301 to spend on shirts and pants. If shirts cost $23 and pants cost $35, and you leave with 11 items, how many did each of those buy? Now this is actually a part of a 4-video series I'm doing in my Algebra 1 class right now. We just got done talking about how to set these systems of equations up from word problems. So I'm going to go through this relatively quickly. I'll put a link to the previous lesson in the video if you want to practice writing equations or systems of equations from word problems. And then again, like I said, we'll be doing system substitution and linear combination here very, very soon. Those links will be in there as well. And we talked before how when you do word problems, you want to read them slowly, you want to pull all that important information out. And clearly we have something in here about money. We have a total amount of money. Some of them for shirts and pants. And we talked about how you want to get to the end of your question and read, what is exactly you're trying to find? What's the unknown? Because that's what a variable is. It's something, a letter generally. So you can use words too that represent an unknown quantity. So if it's how many of each item, then we better make sure we define those variables, which is how many pairs of pants and how many shirts. We have information in here about money spent, so we probably are going to have an equation dealing with a total amount of money. And yeah, indeed, we'll do a dollar sign for money. When you go to the register, you're going to pay $23 for every additional shirt you buy, and repeatedly adding $23 is represented in algebra or mathematics in general, actually arithmetic, with multiplication. So we have 23 times, 23, it's a numerical value related to shirts, and S is the number of shirts, plus, you're going to buy some pants, and every pair of pants is another $35, and repeatedly adding 35 is going to be represented with multiplication, and that is going to be equal to that total bill that we had of $301. What other information do we have in here that is maybe something that we would need to do math to arrive to? Well, let's see. Hopefully we can differentiate between the blue and the green. That's going to be the fact that you bought a total of 11 items. Let's do that side by side. I'm not leaving myself very much room here. Okay, great. So we have our variables defined. We have our equation defined by a total, or giving us a total amount of money. We have an equation that's telling us a total amount of items purchased. And our variables, again, are number of shirts and a number of pants. When you're graphing lines, you're graphing what's called a bivariate set of data, or bivariate data, and you're comparing those two unknowns to each other. So we need to decide which of these two variables are going to be in this graph. I've got a scale now, unlike I forgot to do on the previous one. I need to decide which of these two variables I'm going to put on my x and y axis. And I'm looking down just to make sure that in the end my problem here in front of you matches my notes, and so I can check my work easily. Excuse me. Whew. So we're going to put number of shirts, so myself and whoever's grading my paper, or if I look at this later, I understand what the heck I was doing. I'm going to put shirts along the x-axis. The x-axis is where you put your independent variable. In this case, if we're just buying shirts and pants together, I'm not really sure if there's a clear independent and dependent relationship, where something like maybe if you have a word problem dealing with time, it's almost always going to be time as the independent variable, and something is going to be dependent on how long that's been going on. But if we say number of shirts is going to go along the x-axis, number of shirts is the domain, it's the independent variable, well then if you're buying a total of 11, the number of pants is going to need to adjust, is going to be dependent on how many shirts you buy. Great. Now this time we're going to review graphing with both slope-intercept form and with x and y intercepts. Now this is a nice easy little equation. My number of shirts is on my x-axis, so I've therefore defined it as my independent variable, and my dependent is the number of pants. My dependent is like the answer that you get out of an equation. So I want to solve this for p so that I can match it with my graph over here, and also not make my s's look like 5s. Okay, so my P is now my answer. It's P in terms of S. Just keep throwing different language at you. P, therefore, is the dependent variable. Our slope in front of this S, got a little -1 there. So our slope is -1/1. Our y-intercept is 11, and our y-intercept is 11. Okay, plot that y-intercept first. Our slope is down 1 and over 1. So from here we're going to go down 1 over 1 and down 1 over 1 and down 1 over 1 and just keep that pattern going. I'm going to be looking for an intersection of 2 points, and I've got some numbers that are rather large. So this time I am going to use a ruler. There we go. And since we're doing a word problem, by the way, let's interpret what it means for this y-intercept to be 11. My y-intercept is, again, where my x value is 0. So interpreting my y-intercept in context of this problem of buying pants and shirts is, if I buy 0 shirts, assuming, of course, I've bought a total of 11 items, then with buying 0 shirts, I've bought 11 pair of pants. That's the interpretation of the y-intercept. I can interpret the x-intercept too, which is if I don't buy any pants, I've then purchased 11 shirts. The slope being, -1, for every 1 additional shirt I purchase, the number of pants that I can purchase is decreasing by 1. See, now it would make sense to say this is a sort of in terms of a unit slope. Every time I buy an additional shirt, how much is the number of pants that I'm able to buy going down? In this case, it's 1. Now, if I try and solve this for P, I'm going to have 2 rather uncomfortable fractions to deal with. So this time we are going to find an x and y intercept. And we're going to speed the tape up here to, in a second to shorten it up a little bit. But we're going to find an s intercept by letting p equal 0, and I'm going to do that, of course, with this equation. And we're going to find a p intercept by letting s be 0. So that will be 23s plus 35 times 0 equals 301. And 23 times 0 plus 35p equals 301. Okay, great. So I just, that's 0, and then I divided to undo the multiplication. So our s and p intercepts here are 13.09. And we're going to do this in green. So the s-intercept is 13.09, a little bit past 13. And our p-intercept is 8.6, so a little bit just past the middle of 8 and 9. We're going to connect those dots. And these two lines are intersecting at one particular point. It is right here. And it looks like if we purchase 7 shirts and 4 pair of pants, we are satisfying the condition that we have 7 plus 4 is 11. So we've bought a total of 11 items. Now what we need to do is make sure that when we plug in a S for 7, or 7 for S, 7 shirts, and again, that 4 being the number of pair of pants, that we are satisfying that condition that we're spending a total of $301. Now, doing this math without a calculator, we have 7 times 20 is 140, and 7 times 3 is 21. Well, 140 and 21 is 161. We also have 30, that's the tens place. That's why I'm saying 30, not 3. 30 times 4, well, 3 times 4 is 12, so 30 times 4 is 120. 120, okay, now 4 times 5 is 20. 120 and 20 makes 140 as I look up and kind of just running that through in my head to get one more time to make sure I'm right. And 161, well, we have 140 plus 100 is 240. 240 plus 60 is 300. And yeah, we get 301. And our answer checks out, even though, so we had some kind of complicated decimals there as we were finding our x and y intercepts. But connecting those lines carefully did appear that we were intersecting at the point of 7, 4, and so graphing did help us solve this problem. Now, if I gave us information where we were told the number of shirts and the number of pants, and we're asking how much each of them cost, and with cost values usually being a decimal, like $23.85 or something like that, those type of decimal values, you're not going to be able to, you can estimate with a graph, but not find them accurately. And I'm pausing, let's just make sure I haven't forgot to say anything. Okay, that is the end of my last example. I'm Mr. True. Bam! Go do your homework. And I'm going to get the phone